Logarithmic differentiation versus the product rule. Hello everyone. Let's begin our discussion on logarithmic differentiation versus the product rule. As we dive deeper into the study of calculus, you will notice that we frequently encounter functions that are formed by the product of several other functions. Now, the standard product rule is typically the first tool you learn to handle these situations. However, as we will see in the upcoming slides, this method can become computationally expensive and algebraically tedious as the number of factors in the product increases. In this subsection, we are going to explore why a technique called logarithmic differentiation is often a much more efficient and streamlined alternative when dealing with these complex products. The standard product rule approach. Now that we have established the general concept, let us take a closer look at the standard product rule approach to understand where the challenges lie. Starting with the basics, the standard product rule for two functions, u and v, is defined as the derivative with respect to x of u times v equals u times the derivative of v with respect to x, plus v times the derivative of u with respect to x. This is a straightforward process that most of you are already familiar with. However, the complexity increases when we deal with a product of three functions. If we have a function f of x equal to u times v times w, the rule expands significantly. The derivative of u times v times w is equal to u times v times the derivative of w, plus u times w times the derivative of v, plus v times w times the derivative of u. As you can see, as the number of functions in the product increases to 4, 5, or more, the number of terms we must calculate grows linearly. This leads to a practical problem. The likelihood of making a small algebraic error increases significantly. Because the expression becomes so long, it is very easy to misplace a sign or omit a term. Furthermore, each individual term requires a high level of concentration, as you must keep track of multiple functions while ensuring that you are differentiating only one of them at a time. Given these inefficiencies, it becomes clear why we need a more streamlined method. In the next slide, we will explore how logarithmic differentiation can simplify this entire process. The logarithmic differentiation approach. Now that we have seen how the standard product rule can become algebraically tedious as we add more functions, let us look at a more elegant alternative, logarithmic differentiation. The core idea here is that we can leverage the properties of logarithms to transform a complex product into a much simpler sum. To understand how this works, recall the fundamental logarithmic property. The log of the product of a b and c is equal to the log of a plus the log of b plus the log of c. We apply this to our calculus problem by taking the natural logarithm of both sides of our equation. So, if we start with y equals u times v times w, taking the log of both sides changes the operation from multiplication to addition, giving us log y equals log u plus log v plus log w. Now, instead of applying that complex expanded product rule we discussed in the previous slide, we can simply differentiate each term individually using the chain rule. On the left side, the derivative of log y is 1 over y times di over dx. On the right side, we get 1 over u times du over dx, plus 1 over v times dv over dx, plus 1 over w times dw over dx. Finally, to isolate the derivative we are looking for, we multiply the entire equation by y. This results in the final formula. Di over dx equals y, multiplied by the sum of u prime over u, v prime over v, and w prime over w. While this process involves a few more steps, it significantly reduces the chance of making a manual calculation error. To see this efficiency in action, let us move on to a comparative example. Comparative example. Now that we have discussed the theoretical framework for both methods, let us put them side by side to see which one is actually more efficient in practice. We will differentiate the function y equals the product of x plus 1, x plus 2, and x plus 3. First, let us examine method A, which utilizes the standard product rule we covered in the previous slide. In step 1, we identify our three separate functions. U is x plus 1, v is x plus 2, and w is x plus 3. In step 2, we find their individual derivatives. Since each of these is a simple linear expression, the derivative of each is simply 1. In step 3, we apply the expanded product rule. This requires us to multiply two of the functions by the derivative of the third, repeating this for all combinations. This gives us x plus 1 times x plus 2 times 1, plus x plus 1 times x plus 3 times 1, plus x plus 2 times x plus 3 times 1. Finally, in step 4, we simplify the expression. After expanding the brackets, we have x squared plus 3x plus 2, plus x squared plus 4x plus 3, plus x squared plus 5x plus 6. Combining these like terms, we arrive at the final result, 3x squared plus 12x plus 11. Now, let us compare this with method B, using logarithmic differentiation. In step 1, we take the natural logarithm of both sides, which gives us log y equals log of the quantity x plus 1, x plus 2, and x plus 3. In step 2, we apply the logarithmic property we discussed earlier to transform the product into a sum. This changes the equation to log y equals log of x plus 1, plus log of x plus 2, plus log of x plus 3. Step 3 is where the efficiency becomes apparent. We differentiate both sides with respect to x on the left side. Applying the chain rule gives us 1 over y times the derivative of y with respect to x on the right side. We simply get 1 over x plus 1, plus 1 over x plus 2, plus 1 over x plus 3. In step 4, we isolate the derivative by multiplying the entire expression by y. This gives us the derivative of y with respect to x equals y times the sum of those three fractions. Finally, in step 5, we substitute the original expression for y back into the equation. This results in the derivative of y with respect to x equals x plus 1, x plus 2, x plus 3, multiplied by the sum of 1 over x plus 1, 1 over x plus 2, and 1 over x plus 3. If you observe the two methods, method B might appear longer in the final substitution step. However, notice that the actual process of differentiation in step 3 was significantly simpler and less prone to algebraic errors than the repeated multiplication required in method A. This demonstrates why logarithmic differentiation is the preferred tool for complex products. In the next slide, we will discuss some common mistakes to watch out for when applying this technique. Common mistakes. Now that we have compared the two methods and seen how logarithmic differentiation can simplify a complex product, it is crucial to discuss some common pitfalls. Even though the process is more efficient, there are a few areas where students frequently make mistakes. First, let's talk about forgetting the y factor. As we saw in the previous example, when we take the derivative of the natural log of y, we obtain 1 over y times the derivative of y with respect to x. A very common error is to find this expression, but then forget to multiply the final result by the original function y. Remember, our goal is to isolate the derivative of y, so that final multiplication step is essential. Secondly, be mindful of your logarithm properties. Some students mistakenly assume that the log of u plus v is equal to the log of u plus the log of v. This is a significant error. Please remember that logarithms are designed to transform products into sums, not sums into sums. Always double-check that you are applying the property to a product before splitting it apart. Finally, do not neglect the chain rule. When you are differentiating the log of a function of x, it is easy to forget to multiply by the derivative of that inner function. Always keep in mind that the derivative of the log of u is equal to 1 over u, multiplied by the derivative of u with respect to x. By keeping these three common mistakes in mind, you can ensure your calculations remain accurate. Now, let's move on to the final slide to summarize our key takeaways. Key takeaways. Now, let us wrap up this lesson by reviewing the key takeaways, to ensure you know exactly when to use each method. First, regarding the product rule. As we discussed in the earlier slides, this method is best suited for simple products involving only two functions. However, as you saw in our comparative example, it becomes computationally cumbersome and tedious as the number of factors increases. On the other hand, logarithmic differentiation is the ideal approach when you are dealing with functions that involve multiple products, quotients, or even variable exponents. The primary reason for this is efficiency. By leveraging the properties of logarithms, we can reduce the overall complexity of the problem by converting multiplication into addition, which, as we have seen, is significantly easier to differentiate. Finally, here is a general rule of thumb for your future problems. If you encounter a function that looks like a long string of multiplied terms, do not immediately default to the product rule. Instead, consider using logarithms to simplify the expression first, as this will likely save you time and reduce the chance of algebraic errors.